the involumetry or the involute profile of the tooth. Okay, so again, please, when you have access to these presentations, please try to click this link. It will take you to a nice video that will show you some more information about involute profile of a tooth. Okay, so what you see on the screen here, you see that we have driving gear here and we have driving gear. And this driving gear rotates about this center point, and this driving gear rotates about this center point. Here we are sharing only one tooth each, okay? But the rest is there. It's just a snapshot of one tooth only, right? So when you connect the center point of the driving gear and the center point of the driving gear, the line that connects them, this line here, is called the line of centers because it connects two centers, okay? And then when these two teeth come together, they push each other in order for the rotation to happen, right? So in this case, we have a line here, okay? This line here. This line is called the common normal. Why it's common normal? Because it is normal to these arcs. And these arcs are the involute arcs. So we're going to talk more about this, but these arcs are involute arcs, and this line here is perpendicular to this. So sometimes they call it common normal. Sometimes they call it line of action or pressure line. So it has different names actually, okay? So what happens is that at this point here, at this point, the intersection between the line of action, because the force is transformed between the two teeth along this line, and the intersection between this line and the line of centers, it's called, there is a point called B, and this is the beach point. It is fixed. It is always, all the time, it is in the same location. But here, at this point here, where the two teeth, they come together, they touch each other, it's the point of contact, okay? So in this case, we want to generate what is called the conjugate action. Conjugate action. What is conjugate action? The conjugate action actually, here, if you have tooth profile, which in this case called involute, okay? So this produces constant angular velocity ratio between the two meshing gears. So if you want the, if this driving gear rotates with omega 1, for example, so this is driving 1, so driving, so this is omega 1, and the driven is omega 2. So if you want this ratio omega 1 over omega 2 to be constant all the time, regardless of where this point of contact is, so you have to have a specific profile here for the tooth of the gear. So this specific profile that produces or offers this kind of constant angular velocity is called involute profile. So you can make this as a part of a circle, for example, or any other shape, straight line, for example. So this profile can take any shape. But in order to just produce this constant angular velocity, you have to have what's called conjugate action, and this conjugate action is enabled by using involute curves. Okay, so the involute tooth profile produces a conjugate action, and this is the most common type. So most of the gears, they have their shape, their teeth. They are just profiled using involute shape, okay? And the principal advantage of this, it ensures the center distance error do not affect the velocity ratio. It means that if we have any error between the center point here and the center point here, due to misalignment or due to some errors during installation, etc., so they do not affect the velocity ratio between these two gears. So there is a one way of producing this drawing or involute curve. There is an engineering drawing method of doing this. But what you can see here is a nice presentation of how you can imagine this involute profile. So imagine that you have a cylinder, If you have a string, you can wind the string. Just imagine that this is the end of the string, and then you have a string. Say this is the string, and then you can wind the string around the cylinder like this. Okay, like several ones. Then if you just grab the end of the string here, okay, so this end here, and then you keep the string taut. You keep it taut, right? And then you just try to unwind the string in this direction. Keep it taut, and then try to unwind. This point here is going to follow what's called involute curve, and this is what is shown here. So imagine that this is the string that I was talking about, and this is the end of the string. So, and then when you move from here to here, and then from here to here, and from here to here, you start unwinding this string, but you keep it taut. The point here that you should keep it taut, right? So when you start unwinding this, so the end point here draws this curve, this involute curve. So there are engineering drawing way of doing this. You just divide the circle into a specific number and take tangents, etc. But it's not the task here to learn how to draw this. But it's for you to understand that this is the way we produce involute curves, and we use it to keep the velocity ratio or the rotational speed ratio constant. This, I told you about the base circle earlier when I was introducing the two gears. The base circle is very important because the involute curve starts from the base circle. So when you have a base circle, so the involute curve starts from here. So this is the gear tooth, and then this part of the tooth is involute. And then if you remember, we had another circle. So this circle here, we called it the dedendum circle. So the distance between the dedendum circle and the base circle, it's non-involute. So this part here, this part here between these two is non-involute portion. You will understand why I'm just stressing this at the moment. It is quite important, but later we'll talk about this, okay? So you know that the involute curve starts from the base circle. You should know that, okay? Right, so other involute profiles could be a part of a circle, for example. So there is one more conjugate curve. It's called WN curve, or WN gears, or WN profile. It is named after these two scientists. And then you see here that you have a pinion, and then you have gear, and then you have here the profile of the gear tooth takes a specific shape, either convex or concave, but eventually it just does the same. It just does the same thing. But there are some challenges of producing or manufacturing these types of gears, and also they are very sensitive to center distance error. So if there is an error during installation, and the center distance changed, so this extremely affects the speed ratio. So obviously what we have here, this is just part of the pinion and the gear, okay? So the top one here is the pinion, and the bottom one is the gear, okay? So we have three different types here. We have type A, B, and C, right? If you look at A, it says here the arc of the pinion is convex. So you see here this arc here on the pinion is convex. It's taking convex shape, and the arc circle on the gear is concave. So the arc pinion and the gear here is concave, and this convex and concave shape, they engage together, they come together, okay? And if you take here the tooth of the gear, it shows here the distribution, the load distribution between the tip of the tooth to the root of the tooth, okay? Then the next one is the other way around. So the pinion is taking here concave shape, and the gear is taking convex shape, right? And then the distribution of the load here is different. Here, it's a combination of both. So part of the tooth is concave, part of the tooth is convex. Okay. So for example, this part is convex, concave, and this part is convex. Okay, of the same tooth. And they are similar for the pinion and the gear. And then the distribution here is two parts. For the concave part, the convex part, this is the distribution of the load when they engage together. There is some load between the two teeth, and this is the distribution of the load at the bottom part or the concave part. Okay.